Hello, my guys. How are you doing? I hope you had a very good weekend. And do you remember what we were doing in probability last time on Wednesday when we left? I thought that what I'm asking you are weird questions, right? It's inappropriate, I would say, right? Have you practiced the exam? Have you been solving exam problems? Yes? Hello, Sydney. And hello, everyone else. Several problems, and how do you find those problems? Not by Googling them, yes? You find them interesting, I hope. The next exams are going to be more interesting, I'm hoping. Right? There's so many things. I just my eyes are just running in all directions. What can I ask you? Do you want me to show you the actuarial exam collection I have? Right. So I consider asking lots of questions from there. Some I questions. Well, don't we all? Apparently, I have a very bad effect on unstable people. So I'm like a drug. I first get them destabilized, but then I am the only thing that can get them stable, like heroin. You know, people get twitchy and then they need heroin. That's what hopefully will happen to you as well. So this is a question that I want to begin with, guys, and it is tremendously relevant. I'm not sure if you will see it. I hope to give you those numbers on your exam, on the second exam. Actual real numbers, and see what you will answer about them. And I might disguise this question as something unimportant. Just a curious thing is, how do you think? And would you realize when I disguise the numbers as something unimportant what it is, or whether you would give the right answer in that regard? Okay. So there are a lot of things that happen, and in probability and statistics, there are so many ways to misinterpret information. So let's begin with this example, guys, and maybe it will not confuse you. A kidney study is looking at how well two different treatments, treatment A and treatment B, work on small and large kidney stones. Here is the table. This is what was obtained. Look at this table carefully, guys. And your job is to determine whether or not treatment A or treatment, let's say it this way, which treatment is better? Treatment A, treatment B, are they the same? Which treatment do you think is better? You see? So how to read this table? So looking at the total, you see that treatment A helped 78% of the cases, whereas treatment B helped 83% of the cases. Which of those two treatments do you think is the better treatment? And turn on your cameras, please. Yes, there are many differences here, but let's see if you can figure out what you think. Looking at this data, which do you think is the better treatment? So here is K small, kidney stones, and K complement, that's for large stones. Right, so there, when you treat a kidney against stones, you have small stones and large stones. And if you know about kidneys, you know, small stones, I guess, are much easier to treat than large stones, correct? Well, maybe they're tremendously far apart. Well, maybe not. I mean, that's not so important, not far apart or not. You just let's say the difference is significant. Which treatment is better? Holistic treatment grant is when you solve at least a problem a day. And he doesn't. Yes. Okay, guys. So imagine you need to compare those treatments, and let's say the results here are significant. You know, the true investigation is even so much harder. As some of you are saying, okay, are those results significant? That's an important question. What do they mean? Such interpretations are very difficult. I mean, I can make it a very dangerous conversation if you want to, right? In today's day, I mean, right? What things are sensible, what are not? How can you judge? So you look at those treatments, guys, and some of you are beginning to notice something important here. So if you break it into categories, you can see that treatment A worked in all for the sample of people against small kidney stones worked 93% of times, right? So treatment A against small kidney stones worked 93% of the time. Against small stones, treatment B worked less well. Do you agree? Against small stones, treatment B worked less well. So when faced with small stones, which treatment do you prefer? Treatment A or treatment B? Okay, interesting. Treatment A. Now, against large stones, which treatment do you prefer? You see, notice there, both of them are less effective against large stones. That's a more difficult problem. Which do you prefer? A. So which is the better treatment? Exactly. It is treatment A. Now, you see, guys, I mean, we ignore at the moment, complexities, of course, what is, you know, I mean, the sample sizes are not the same, right? And I can consider, I mean, I will see if I will give you those examples about actual statistics. That's what maybe I will plan to do on your next exam, give you actual statistics, and then decide whether to tell you an actual reference of this information or not. Right? I will think about it, because I do want you to realize, in some sense, what conclusion do you reach when you're not biased? And maybe also I would be very interested in knowing what conclusion do you reach if you are biased. So in this case, guys, just by looking at the percentages, it looks like against each specific treatment, against each specific challenge, treatment A is better. Then you see, but overall, treatment B appears to be better. Now, why is treatment B appearing to be better? It cured more cases than treatment A, but the cases are not of the same proportion. You agree? I mean, if I give one person exam A and another person exam B, and a person doing exam A fails, and a person doing exam B receives 100, is it meaningful? Unless the exams are of the same difficulty, it is not meaningful. Do you agree? Perhaps exam A was Putnam, and you have notoriously complicated questions on the Putnam, and exam B was just the basic arithmetic. You understand? So you have to always compare. That's a very difficult principle. You must always compare like with like. You understand? Always compare like with like. In other words, you cannot, when you do comparison in statistics, you cannot compare one country with another, not truly. You have to compare the country with itself. You have to control as many parameters as possible to see if you have a meaningful result. But the principle is always compare like with like. So for instance, you have in the media, you compare the current epidemic with 1918, with the influenza of 1918. And if you look, for instance, at statistics in Britain, you will see that in Britain in 2020, the number of people that died, right, the total number of people dead in 2020 matches more or less the total number of people dead in 1918. Yes, and then if you read some papers, they make this very big claim that it's the same, because, well, it's a very, you know, they say, well, it's just, we have not seen such death since 1918. It's the biggest amount of death that you've seen in 2020. Is it a meaningful result? And the answer is no. Why is it not meaningful? Because in 1918, let's say one reason, the population was much smaller than in 2020. So if you do not normalize by the population, you're not comparing like with like. You see, you have, and even if you, of course, there are many other differences between 1918 and 2020 naturally, but you try to minimize all those differences. You try to make them standard. Okay, so there are so many ways you can reach so many strange conclusions and interesting conclusions. So this is known, by the way, as Simpsons Paradox. Okay, and in Simpsons Paradox, you can show, for instance, that poison is very helpful to you. You know how you can do that? Here is a simple example. I'm going to draw an idea, right? So imagine that I give you a hypothetical poison in the studies, right? So imagine that we have young people and old people. So this is what you observe. I'm just going to give you this hypothetical drawing. So this is basically what you observe is that for people, you note the amount of medication that you give people and how well they feel. I mean, how much better, how much they feel, right? So there is some sort of, let's say, ranking of how well they feel. So let's say initially young people, they feel very well. The younger you are, the happier you are about your existence. You're not upset about anything, right? And then as you get older, you have more and more ailments and your life is not as good as you hoped it will be. And there are so many disappointments and you don't feel as well. So you see this trend, right? You see that young people, let's say they are gathered in terms of how they feel. They are gathered like this. And old people, no, actually, let's say those are this is how people feel, and as you can see that in this young population, as you increase the intake of the medication, young population, it appears that they're feeling worse. So this medication is poisonous, right? Now, old. This is, let's say, sorry. Let me do it again. I said I was not planning to do it, and of course I speak in a confusing way. Here is the data that you have here. So you have, let's say, the blue dots. And you have the red dots. So, so the red dots are higher in general than the blue dots. Red dots, those are, this is the healthy, the health condition of young people, right? And then what happens is that as you increase the amount of intake in medication, you can see that there is a drop in feeling well for old people. There is a drop in feeling well for young people. But if you did not distinguish between young and old people and lump them all together as one population, yes, what would you see? You would see a somewhat positive correlation. You would see something like that. Do you understand? You would actually reach the conclusion that this medication helps a person feel better, even though you're just poisoning somebody. That's an example of Simpsons Paradox. Do you understand what I mean? Right? What really happens here is for each age group, for each age group, this poison that I'm giving is making them feel worse. But because young people initially are feeling stronger and they can take more poison, their reduction in health is not so significant, and it offsets the more significant reduction in health of older people. And altogether, the offsetting actually can seem like it's balancing to the top, and you can reach tremendously incorrect conclusions this way. Well, pretty much. You can lie with statistics and make money. You can even lie to yourself. You can be just confused. It's very, very difficult to know what is true, what is correct, what is not, and very difficult to notice certain very subtle things. And if you spoke German, I can show you very interesting videos about it. I'm sure there are similar ones for in English, but I am aware of German things. Well, I don't need to train the next generation of flyers, my friends. I'm sure you're already pretty good at that without my help. Good. So this is known as Simpsons Paradox, and there are many interesting cases, both in courts. You understand? People were convicted and sent in prison on results like that. There's prosecutor's fallacy. There's a very most common thing that sends people to prison incorrectly. And there is Simpson paradox, which just makes you reach incorrect conclusion because you did not compare like with like. Yes. An example of Simpson's paradox, another thing I want to say is, for instance, there was once, I'm not sure if it's very recent or not, an accusation against, I think, Berkeley University that they are misogynistic and they accept males more frequently than females into college, right? And that was just the same thing over here. So what really happened is that if you compare population, you understand, if you compare by population, then it appears that let's say more men are accepted than females. Right, I can send you a video, but what you have to do, this is what you have to do. You cannot compare men and women. You have to, if you want to reach this distinction, you have to compare what percentage of men that apply get accepted compared to what percentage of women that apply get accepted. You understand? So if you compare the male and the woman population like this, then you will reach an incorrect conclusion. You have to compare women to women. In other words, women that are accepted to women that applied, men that accepted to men that applied, or else you reach an incorrect conclusion. Yes? So this thing happens very, very frequently. So here is another interesting result, guys, that maybe you knew, maybe not. Anyone speaks Hebrew? No? In ancient Jewish law, if you had a trial, so rather you speak some Hebrew. There is a recently interesting movie I've seen, sorry for the interjection. I think I saw it yesterday. It's called A Serious Man. It was a bit odd, but in light of movies that I've seen so far, it's better. So it's about a Jewish guy in, yes, Coen Brothers, exactly. Check it out, guys. Maybe you would be interested. It really got me excited. As you see on the board, the guy is writing quantum mechanics, right? Which involves probability. So back to this thing. In ancient Jewish law, a suspect that would be unanimously convicted by all the judges will be let loose, free. You understand? So if all the judges convict you, you are released to freedom. Now, why would that make any sense? So this is a difficult question, so take a deep breath. Yes, bias. So suppose that there are n judges that decide a case, and suppose that there is a probability P that a suspect is guilty. Would anybody like to explain to me what it means that, let's say, the suspect is guilty, the likelihood that the suspect is guilty before the trial is 60%. What does it mean?
There's a 60% chance he actually committed the crime, or is it there's a 60% chance he's going to be convicted?
No, conviction, let's say that he convicted the crime, but what does it mean that there is a 60% chance that he convicted the crime?
Right.
Yeah, that's what I'm asking. Yes.
6 times out of 10. Yeah, what Nicholas said.
Exactly. That's very good, guys. Maybe you can come up with better ideas, but those ideas at least allow me to think about it. You understand? When I think and it's hazy, I don't know what to say about it. But what I imagine is that there are whatever number of universes, and in each universe is equally likely. And in 60% of those universes, this particular person is guilty of the crime, committed the crime, not necessarily convicted, right? So P is the initial probability, and any other evidence will tell me in which portion of those universes we find ourselves. So we might find ourselves in some portions where it's even more likely that he is guilty. Yes, you agree? That's the idea. You see, because you take pieces, basically you have this space of universes, and each new information removes some universes out of that space, and from that reduced sample space, the reduced number of universes, it might be more or less likely that this particular person is guilty. That's the evidence, right? The evidence is with those universes where the person is guilty, and we found this evidence, right? So how many of them do we have? And how many universes we have where the evidence is found and the person ends up not guilty? So that's the conditioning that we do there. So suppose that P is that initial probability that he is guilty, and we have n judges. N might be 100, 200. You know, the more the better. The more people judge, the more likely a person is innocent. You might imagine. The more people say the same thing, the more likely there is something terribly wrong. That I hope you already understand. Right? So that's what bothers me in the last time. The more people are absolutely saying the same thing, the more it's likely that something is just not quite right. So n judges, so basically what we have, if there is a systematic error, we simplify a little bit, right? So there is some probability, we don't know it, but there is some probability S that a systematic error occurs. In other words, a probability S that there is a bias. You understand? And if there is a bias, the person is convicted regardless of whether or not he is innocent or guilty. Let's say somehow if there is a bias, it does not matter. We're assuming some sort of slack here. Yes? And let's suppose that when the person is guilty, each judge, and there is no bias, right? If there is no bias in each person, and the person is guilty, each judge will convict with probability C. The numbers are summarized here. It's a bit hard to read it all, but you see, this is the initial probability of guilt. This is the probability of bias, and C is the probability of convicting correctly. In other words, if the person is guilty and there is no bias, the probability of correctly convicting is C. And if the judge is competent, it should be more than 1/2. And W is wrongful conviction, right? If there is no bias and the person is innocent, there is also a possibility of wrongly voting to convict. And let's say if the judge is confident, this is a number smaller than 1/2. And that's true for every judge. Make sense? So W less than 1/2 and 1/2 is less than C. That represents a proper trial. Yes? So then let's consider the situation. Suppose that exactly K out of n judges vote to convict. So exactly K voted to convict. I mean, under our simplifying assumption, that means there was no bias. Not everybody convicted, right? So K is less than n. If K of them voted to convict, what's the probability the suspect is guilty? Yes, so we're solving A first. So let's try to understand how to set it up. So CK for any K is the event that K out of n judges vote to convict, and J sub I is the event judge I voted to convict. I just have those labels. Did I use J? I don't remember. And then B is the event of systematic bias, and G is event that the suspect is guilty. So what we're interested in is probability of G given that K judges voted to convict. And I hope you already are comfortable with this. That is the same as the probability that K judges vote to convict given that suspect is guilty times the probability the suspect is guilty divided by K judges voting to convict given suspect is guilty. And then here is the same thing given that the suspect is not guilty. Yes? So this formula makes sense to you, correct, guys? So far, this line makes sense. Yes, that's the standard thing that we do is usually if one way of calculating conditional probability is uncomfortable, reversing it can make it easier. So CK given G is easier to calculate than G given CK. So that's what we do in the right, correct? And then the probability of this probability that that K votes to convict, we're assuming the judges are twins, and each then has to vote correctly to convict or incorrectly to acquit. Incorrectly 1 minus C, right? So because they're twins, I can say, well, who voted to convict? There are n choose K possibilities for the judges that voted to convict. You agree? So it's either judge 1, 2, 3, all the way to K, or any other choice of those that vote to convict, and the rest vote to not convict. And they function independently. So n choose K, look at it. So because they're all the same, it's the same as n choose K times the probability that judge 1 through judge K voted to convict, and everybody else voted to acquit. Are you still with me, guys? Do you understand how I got this line? Right? I just added up lots of probabilities that are the same number, right? So so that I might just multiply this one probability by n choose K. And then what is this? By independence, which we're going to, by the way, cover more thoroughly in a moment. I mean, maybe today, maybe next lesson. That's the same as C to the power of K, because judge 1 votes to convict, it's C. Judge 2 votes to convict, given that judge 1 voted to convict, it's still the same. The judge 2 does not care about the judge 1 convicting. So it's also C. So it's C to the K times 1 minus C to the n minus K. Good? And similarly, this is the probability of wrongfully convicting. Right? So if the person is not guilty, their probabilities are different, but independent of one another. Right? And what do we get? Once we divide, we get this number. Well, I mean, you can understand it. Just this number over that number, you get this number. For now, we leave it alone. Yes, that's the number we get. Now we are interested in B. Suppose that all the judges voted to convict. So now there is a possibility of bias. Somebody actually today returned from jury duty. They should now understand it better. So what is the possibility of bias? So we are going to calculate probability of guilt given that all the judges voted to convict. Yes? And now what is that? Let's be careful here, guys. So then I have to be sure whether or not there is or isn't bias. Yes? So this is the same as probability of guilt and all convicted. Guilt and all convicted, and then bias or no bias. You agree? So it's, what do? I take probability guilt of and convicted divided by probability of convicted of all the judges convicting. Yes? Are you with me? You're understanding the formula, guys? And then I skipped several steps. So maybe I will write it just to be sure. So what is this? This is probability guilt and n people and judges convicted divided by probability of n judges convicting. Yes? And then what do I do with the numerator? I insert B and not B. In other words, that happened with bias or that happened without bias. Those are disjoint events, so I can add the probabilities. Yes? And then probability of Cn. I mean, under which condition did they vote to convict? I mean, there are several things I need. Either guilty or not guilty, either bias or not bias. So there are 4 possibilities. Do you see? So all those are four possibilities for guilty, not guilty, bias or not bias. We get 4 scenarios. You can understand how I partition it. So I just insert, for instance, well, you understand how to do it. I don't need to over-explain, correct? You understand that that you can just further break it apart. Cn, I can break into, for instance, CN and guilty plus CN and not guilty. And then each of those I can break additionally into 2 segments. Yes, every combination of, because I mean, denominator is the probability of conviction. Now, probability of conviction happen in universes where the suspect is guilty or not guilty, and also in universes where the suspect, where there is bias and there was no bias. So there are actually 4 categories based on the 3 properties, on the 2 properties, bias and guilty. Yes. Good. And then I just need to calculate each of those. I need to calculate this one, probability that guilty and bias and all of them convicted, right? If guilty, bias, or convicted, so it's the probability of guilty times the probability of bias given guilty. But we're assuming guilt does not influence bias for simplicity, so that's just probability of bias, times the probability all votes to convict, given that the suspect is guilty and there was bias. Well, because there was bias, doesn't matter guilty or not, the probability is 1. So this is PS. Good. Now, the next one is probability of guilt and no bias, and everyone votes to convict. Again, we do the same calculation. Since this is the probability of all guilty, probability of there not being bias is just 1 minus S, doesn't matter guilty or not. And then all voting to convict correctly, because he's guilty, is C to the power of N, right? There was no bias and he's guilty, so the probability they will all vote correctly is C to the N. So it's this number, correct? And then we calculate the third universe, not guilty, bias, and everybody convicts. Not guilty is 1 minus P, and then S times 1. And then not guilty, no bias, and everybody votes to convict. That means everybody made the wrong decision to convict, and it's this number. Yes, I hope you can. Hopefully, you can do it on your own as well. It's one of the more difficult Bayesian analysis. Right? Some of them are easier, some of them are more difficult. This is among the more difficult ones. And now this is the formula that we get. Now notice what happens, guys. If N is very large, and the probability that each one is correctly convicting is smaller than 1, of course, right? So if N is very large, then this number goes to 0. So that means that the probability that S plus 1 minus S times S to the N, this number just approaches S. And similarly, the other thing just approaches S. So that means that, look at this formula. This is the guilty given that everybody convicted. This is the formula. And I have S plus 1 minus S times Cn. Now, when I take the limit, it will be PS divided by PS 1 minus PS. Yes, which is just P. You see what just happens here? Because if there are many people that vote to convict, that makes it more likely that there was a bias. And if there was a bias, there is no increase in the probability that the person is guilty. So it's as if the trial did not take place. Yes, and that of course makes you wonder in every situation, no matter how much you're convinced that a person is guilty, if everybody is deciding to convict that person, you should know as a rational person that something is wrong. No matter what you think, no matter what's your attitude to a particular situation, if you believe in the due course of fair trial, and you know of situations when a fair trial cannot take place, that means that there was no trial. I do not know if the person should be released. That's a different story, but that means that the trial was just a sham trial, just a demonstration, but no, nothing was gained, no evidence was presented in a sense. Good. So here is something lighter. Ready, guys? Are you still following me? Now, here is a game where you have 3 cards. One card is colored, 2 sides are colored black. One card is a mixed, colored on one side black, on the other red. And the third card is colored red on both sides. So this is the game that we play, guys. I will take one of the cards at random, lift it out, place it on the table, and show you the side. Okay. So let's say the side that it shows is red. I am going to bet that both sides are red, and you will bet that it's the mixed card, that one side is, that the other side is black. Okay, if I pull a card and place it on the table and you see that it's a black side on the table, I bet that both sides are black. I bet it's a homogeneous card, and you bet it's not. Yes? So my question is this a fair game, or does one of us have an advantage? Is the question clear? I always have the advantage. I'm older and more experienced. But calculate, tell me what's the probability I win and what's the probability that you do? And if you want to see, the probability thing I mentioned in German, you might be able to turn automatic subtitles. It's pretty interesting. It's called, well, you let me know. You can write me in the messages if you want, I'll send it to you. Okay, Raider, you message me in the email, I'll send you, okay? I don't want to bother people that don't want to see something. Okay, Nicholas. Interesting. So here is, guys, one thing you should consider. When you see something, right, that happened, in other words, if you see that you see a particular feature, then it's more likely that the other side, how should I say that, has that feature as well, right? In other words, when you see somebody flash $1,000, it's more likely that he has another $1,000, right? If he flushed it in his left pocket, then it's more likely he has it in the right pocket in some sense, right? That's a sense you have in probability. Very good to know for the future, correct? So this is the situation, guys. So I solved it in several ways, and the answer is, in theory, could be slightly more complicated than 2/3. So suppose that this is the situation. Suppose that R is the event that the upturned side is red. Right. So first, guys, I'm not sure. Maybe I already spoiled you. You're jaded, and nothing surprises you in probability as much as it might have before, or you were jaded even before you met me. But here is how many people think, right? So clearly that if, let's say, I show you a card, and without loss of generality in this particular round, the side you are seeing is red. Yes, if the side you are seeing is red, that means that it could not have been this card. It could not have been this card, yes? So then there is either this possibility or the other possibility, correct? So then people say two possibilities, therefore the game is fair, 50-50. Yes, but you have to remember, it's true that there are only two possibilities. It does not make the two possibilities equally likely. Yes, just as I mentioned, winning the lottery or not winning the lottery are two possibilities, but one is much more likely than the other. So how do we calculate? So one way is to set up symbols. So let R be the event that the upturned side is red. And we want the probability of this card 3 being given that I see a red side. Yes? If I see a red side, I want to know what's the probability. It's card number 3. So I mark it in symbols this way. So what is that? That's the probability of seeing red given card 3 times the probability of card 3 divided by probability of seeing red given card 3. Probability of card 3 plus probability of seeing red given card 2, probability of card 2. Those are the two possibilities, yes? Now, what do I know? I know that the card was selected randomly. So it means that probability that card 3 was selected is 1/3. And probability that card 2 was selected is 1/3, so I can cross them out of consideration. And I have this probability, right? And obviously I will see red if it's card 3, so that's 1. Now, what about if it's card 2? Well, provisionally, I will say that's probability P. What's the likelihood you will see red if it's card 2? If I am not aware, if I do that randomly and I place the card randomly face up or face down, then of course that probability is 1/2. But in general, maybe I am aware of something. Maybe I really do not like the color red. And if I can, I will show you black. Or I really like, some basically I have some biases or some quirks. And if I know which card, I will have preference or how to place it. Yes, so in general, this is probability P. And if P is equal to 1/2, yes, if P is equal to 1/2, in other words, we pull the card randomly and I am not looking at it until it's placed on the table, then 2/3 is the result. You agree? Very good, Barry. Very good. You understand how 2/3 came around, but in general, it could be a different result. Here is what can happen. I mean, in general, if P is not, look at it, if it's card C2, if P is, for instance, if P is equal to 1, right? Maybe whenever I have an ability to show you red, I will always show you red, right? Then the answer is 1/2. It could be. You understand that this is the more general situation. In other words, under the assumption that I pull the card randomly and place it on the table, it's 2/3. But if I actually, before showing you the card, look at it, and I know that which card it is, and I think, okay, whenever I have red, I would always show red, and you know that, then the probability actually is 1/2. Make sense? So it's a bit more complicated. Now, you can also solve it in another way. It's very similar to Monty Hall, and we are going to consider all those questions. Yes, they are very similar ideas, and yet they have some slightly different flavoring. So another thing is we can do that also this way. We can imagine that we record the caller on one side and the caller on the other side, right? So side visible and side not visible, right? So we can simulate it using a Kafka protocol, side visible, side not visible. Yes. Now, what is the event read? Event read means that I have the visible card is read, right? So in the case of there's one card that has a red black, that means that it's red and black. It's I labeled one side as 1 and 2, and then red 2, black 1. That's the visible, that's the invisible side. Or if it's card C3, there are two possibilities of making red visible. Do you see that? So red has has 3 universes. If red is visible, then there are actually 3 universes. And one universe is where this is the card. This is not only encodes the card, but which side is visible, or this is the card, right? Do you see that why it's 2/3 by Kafka protocol? Each of those universes is equally likely. Good. That's even faster. You can right away see that it's 2/3. And here is yet another question, guys. We have 3 prisoners. Again, as you notice, similar to Monty Hall, 3 prisoners, and one of them was randomly chosen to be executed. Yes? Thank you. One of them was chosen to be executed at random, and the prisoner in cell 1, he is a bit smart, and he wants the jailer to let him know which of the other 2 people are spared. Right? Give him one name from among the other 2 that are spared. Now, now there is an issue. Will knowing this information affect the probability that prisoner 1 is executed? Yes, so that's the question. And you have to think about understanding this question, right? So if prisoner 1, let's say, here's, oh, person in cell 3 is not being executed, does it affect his estimate of being executed? Calculate and think about it. Okay, Barry, thank you. We shall see. Notice that prisoner 1, he is staying in his cell. Ready? All right. So I'll show you how I solve it, and then you'll tell me if you agree with it. So I will represent by E sub I the event that prisoner I is executed, and we know that probability prisoner I is executed is 1/3 for each prisoner. In other words, if you look at the universes which person is executed, there is exactly one universe in which prisoner 1 is executed, one where prisoner 2 is executed, and one in which prisoner 3 is executed. And each of those universes is equally likely, yes? And then we want to know what's the effect of, because we are not gonna consider universes where we have two information. We have several information. One of them is the name, right? So jailer names prisoner 2 as the one pardoned. Okay, you understand? So there is universe. So I want to know if in some universes he will name prisoner 2, in some universes he will name prisoner 3. Right? And you can see there's clearly symmetry between those universes based on the information that we have here. Or maybe there is no symmetry. That's why we should be careful, right? Because they're not the same people, guys. There is only symmetry if they're twins and everything about them and their crimes is the same. Yes? But let's see if this information affects the situation, then there is no symmetry. Do you agree? Because think about it, guys. If there is symmetry, we look at the universes where one person named, and then person 1 is executed in the same proportion of those universes as where person 3 is named. Correct? So we are going to say what's the probability that prisoner 1 is executed given that second person is named. That's the same as probability second person is named given prisoner 1 is executed times probability prisoner 1 executed. And then the second person named given E1 named, probability of E1 executed, second person named given that he is the one executed, probability he's executed, plus probability second is named when E3 is executed. Yes? And of course, we can erase the probability of E1, E2, E3 because they are the same, and we have this number. Yes. And then what do we know about the top? So I do not know this number. I do not know what's the probability that if there is a name given and person 1 is executed, the jailer can name person 2 or person 3. So I don't know what's the probability that person 2 is named. So I'm going to say it's P. Yes. And if it's P, then the bottom is P. This middle number is 0. You agree? Because there is no condition that allows person 2 to be named as the one pardoned if he is executed. And in this situation, the probability is 1. Do you agree? If person 3 is executed, then the jailer has to name person number 2. So it's P divided by P plus 1. That's what I know about this question. Now, if the jailer has no bias, that means that in universes where person 1 is executed, it's just as frequently person 2 is named as person number 3. And then this probability P is 1/2. Do you agree? You agree that there is an issue of bias here, right? There is no symmetry. Person number 2 and person number 3 are not the same people. And maybe there is not the same reaction to them. Maybe the jailer is friends of prisoner 1 and he knows that I kind of, if I'm prisoner 1, I am friends with prisoner 2, right? Or and he would not want to tell me that prisoner 3 is released, because then I'll be worried about prisoner 2 being executed. We know that it's one of us, right? So there could be so many possibilities there. So in general, it's probability P. You all understand, guys? If person 1 is executed, there is a choice. In the universes where person 1 is executed, in how many of those universes person number 2 named as the one released, and in how many of them it's person number 3 that's named as the one that is released. If the numbers are not the same, then there is bias. So here we're assuming it's 1/2. Yes. Are you with me, guys? Right, you can imagine how many universes there are by just okay, each universe where person 1 is executed, there are 2 possibilities, right? There's a universe where person 1 is executed and person 2 is named, person 1 is executed, person 3 is named. Yes. And yes, and then for each other execution there's the same partition. So then what do we have? We have that if this probability is 1/2, then the probability, this information is not affecting the probability at all. But if the number is not 1/2, it will affect. Right? So for instance, if this number is 1, then the probability is now 1/2. If whenever the judge has whenever the jailer has the option of naming the other person as person number 2 and that's 1, probability of that is 1, then we have that 1/1 plus 1 is 1/2. Are you following me, guys? But in general, if there is no bias in naming, then the probability remains the same. The information is not affecting it. And finally, Monty Hall. Prize is behind one of 3 curtains. Contestant picks one of the curtains, and then the host of the show opens a curtain where the prize is not located, one of the others. So let's say if the contestant picks curtain number 1, then either curtain number 3 or curtain number 2 will be opened. And then the contestant has the choice to stay with his initial selection or change it and pick another one, pick the other curtain that remains. Make sense? So the question is, what should the contestant do? So Nicholas, in the previous question, you cannot truly solve it because I need to know certain probabilities. I need further assumptions, right? So I would interpret, I'm not sure how others interpret this prisoner situation, but I interpret it as follows. If given that prisoner 1 is executed, the jailer is equally likely to name prisoner 2 and prisoner 3, right? One of them is equally likely to be named. Then the probability remains the same. But if whenever person one is executed, there is a bias to name some one of those prisoners, then it could affect the probability. Under the assumption that jailer doesn't care about any of them and names them at random, right? Just throws a coin. For instance, imagine what the jailer can do is given that person one is executed, he will throw a coin, and based on the outcome of the coin, decide to name prisoner prisoner two, or prisoner three. Yes. Then the probability is not changed. Then prisoner one will not gain. The probability of being executed will not change. Good. So if you do it this way by throwing a coin, then you can guarantee that it doesn't matter. So now with the curtains, what do you think, guys? Do you stay? It's very famous. You probably know it. And then if you should switch or should stay, tell me why. Tell me what's the probability of winning if you stay? What's the probability of winning if you switch? Yes, you have the choice to switch curtains. You understand what happens, guys? Yes. So you select a curtain. Now the price is behind one curtain. So either you selected the price or you did not select the price, but there is always an available curtain. The host of the show knows where the price is located, and therefore the host of the show can always open up a curtain where the price is not located. Moderator, it's good that you're in my class, because maybe it doesn't go from 1/3 to 1/2. Question is clear? Yes, guys. I want to know if I should switch or should I stay with my initial choice. Okay, Gustavo wants to keep the curtain. Or is asking me to tell. Well, that's better, Barry, yes. More assertive. All right, let me show you my analysis, guys, and you let me know if you agree. Right? It's not only if you switch or not. I mean, I want you to see if you do that rationally. So let's calculate the strategy. So WS is the event that you win using the strategy of switching. You understand? So that means whichever curtain is opened up, you move to the remaining one, right? So what's the probability you will win by switching? Okay, well, CK is the event price is behind curtain number K. Yes. So suppose without loss of generality, you chose curtain number 1, correct? So you switch from curtain. So either the price is behind curtain 1, 2, or 3. So if the price is behind curtain 1, your switching strategy fails you. So that's where you get 0. Probability of winning if you switch, then it's 0 times 1/3. Now, if the price is behind curtain number 2, that means curtain number 3 was open, and your strategy of switching will be 1. You see, you condition, right? And finally, if the price is behind curtain 3, of course, you again win. So here it is 0 times 1/3, 1 times 1/3, 1 times 1/3, and the probability of winning is 2/3 if you switch. Yes? Does it make sense, guys? And of course, if you stay with your choice, the probability is you can just prove the same way, or just you see, if you use the strategy of staying with your initial choice, then what happens, right? You stay with your initial choice, then price is here, you win, right? Plus stay with the initial choice, price is here, 1/3 probability the price here, you lose, so it's 0, and 0 if it's in the third, right? So what this thing does when in Monty Hall, when you open the curtain, what happens is that 2 doors collapse into essentially 1 door, because you move to whatever remains. So that's why you have twice, you're twice as likely to win if you actually switch. And the more doors, the more potent that is. You see, imagine you have 100 doors, you pick door number 1, and 99, 98 or whatever number is open, and you just have this choice between the door you selected and the other one. It's very likely that the price is behind the other one. Tremendously likely, yes? So it's even more important to switch. Clear? And those are, of course, some people get crazy because of such things that I do. The following example was related to me through the book, The Grapes of Wrath, via a very helpful dwarf. I'm not going to explain what I mean by that, but I will explain the example. Write any 2 numbers on 2 separate sheets of paper. And those can be any real numbers, positive, negative, irrational. You can write pi and √2 if you want. They are just 2 numbers that are not identical, 2 distinct numbers, yes? And what we have is this. So I will pick one of those sheets, and I look at your number, on one number. I don't see the other, okay? And I'm going to use my psychic abilities to gauge whether or not the other number is bigger than the one I'm looking at or smaller. You understand? So I see one number. Let's say maybe you selected the numbers 1 and 2, and I don't know what you selected. I take a piece of paper and I see the number 1, and I need to guess whether or not the second number is bigger than the one I'm looking at or smaller. Yes. Now, who has? So if I guess, then I get the prize, right? And if I don't guess, then I lose money. So who has an advantage here? It's a difficult question, guys, and time is running out. So let me tell you, I have the advantage. Now, why do I have the advantage? Think about what I can do. Okay, guys, so what I will do, I will use the following strategy. So let's say take the normal distribution. Normal distribution can produce any real number. Yes. And I will use this on any other distribution that can produce any real number. I will use it to generate a number, random number. And let's say that random number is k. Yes. And I will use that number as I pretend that this number is the second number. I see your actual number and I pretend k is the second number. If k is bigger than the number that I am looking at, then I'm going to say your number is bigger. And if k is smaller than the number I'm looking at, I will say your second number is smaller. You understand? I will use the random number as a substitute for the actual thing you wrote on a piece of paper. Now, why will that give it an advantage? Well, will it give me an advantage? I'm sorry. So let's suppose, but we have three events here, right? Either the other number is, so either both numbers are smaller than k, or number k is in between the two numbers, or the number k is bigger than both numbers. Do you agree? Either k is smaller than both numbers, or in between, or bigger than both numbers. Okay. So then my probability of winning using the strategy is probability of winning given strategy A, probability of strategy A plus probability of winning given strategy, winning given B. B is not a strategy, I'm sorry, right? It's just a situation, meaning that what's the likelihood I will win given that k is actually smaller than both numbers, right? And vice versa, okay, and then onwards, right? Win given that the number k is between them, and win given that the number k is bigger than both. Now, what's this probability? This probability is 1/2. Do you agree, guys? Because if I know that the number k is smaller than both numbers, right? Here is a number I see, here is another number. If it's smaller than both of them, then either the numbers are like this or like this. And each possibility as far as just the same as it used to be. So a probability is 1/2. In general, not necessarily against you, but reals are uncountably infinite. Right? So not countably infinite. So this probability is 1/2. Yes? Now, similarly, the probability that I will win, given that the number I generated is bigger than both, is 1/2, because you see the number is over there. I do not know, again, it can be this pattern or it can be this pattern, right? This is the number I observed, this is the number I don't know, right? So it's either this pattern or it's this pattern, and where k is located doesn't help me with that at all, obviously, right? So it's 1/2. Unless I mean, if I play against many people, it's 1/2. Maybe against you, it's not, right? Maybe you have a preference and I know something, you know, but this is the situation, right? But where will the strategy always work? If it's in between, right? If it's in between, the probability is 1. Now, why? Let's say it happens that the observed number is bigger. I know k is in between, then my strategy tells me select a number, say that the number that I observe is bigger, right? So k serves as a good substitute, because all I have to do is say bigger or smaller. So k is smaller than y, so the unobserved number is smaller than y. Same thing, right? So I win. On the other hand, if the observed number is the smaller of the two numbers, right, and k is in between, then I would say go higher, go to the right. You see here I say go to the left, here I say go to the right to find the other number. So here again, I will find the other number on the right correctly. So in case B happens, the probability is 1. So then that's what we have now. So probability of winning is now what? It's now 1/2 times probability that that the number I select is the number K I generate is below both, plus probability B, plus probability 1/2 times the probability C. You see this? This is what I get. Those probabilities I don't know. I don't know what's probability A, probability B, or probability C. But what do I know is that probability A plus probability B plus probability C equals 1. Yes. So here I can spare a 1/2 B. So what you have here is 1/2. This is times 1 plus 1/2 B. And you can see this is bigger than 1/2 because probability B is not 0. So it might be very slightly bigger than 1/2, but it's bigger than 1/2. So I have maybe a slight advantage, maybe a very big advantage, but definitely always an advantage. Interesting? Yes, well, that's very nice. So I'm about to end the lecture, guys. Again, if you're interested in that video, it has to, first of all, the video is about 1 hour and 20 minutes long. It's interesting. It's involving statistics. I can afterwards explain to you the gist of it if you're very interested. And it's in German. But I noticed that on your computer you can turn on synchronous translation. I think maybe for that video you can do the same. And if you're interested even more, there is also a sort of rebuttal to that video. So somebody else made a sort of fact check to that video, which both of them are interesting, and it will be very interesting to know for me, what do you think of the information in this video? Right, so there is Volksverpetzer who made a sort of rebuttal, and there is this guy that went and did some sort of statistical analysis. So if you want to see any of it, I don't want to bother you unless you don't, you send me a message on email. Good? Take care.